In mathematics, a finite field, a Galois field, surnamed in honor of Évariste Galois, is a field that contains a finite number of elements. As with any field, a finite field is a set on which the operations of multiplication, addition, subtraction and division are defined and satisfy certain basic rules. The most common examples of finite fields are given by the integers mod p when p is a prime number. Finite fields are fundamental in a number of areas of mathematics and computer science, including number theory, algebraic geometry, Galois theory, finite geometry, cryptography and coding theory. Definitions, first examples, and basic properties. The number of elements of a finite field is called its order. A finite field of order Q exists if and only if the order Q is a prime power pk, where p is a prime number and k is a positive integer. All finite fields of a given order are isomorphic. In a field of order pk, adding p copies of any element always results in 0. That is, the characteristic of the field is p. In a finite field of order q, the polynomial xq minus x has all q elements of the finite field as roots. The non-zero elements of a finite field form a multiplicative group. This group is cyclic, so all non-zero elements can be expressed as powers of a single element called a primitive element of the field. In general, there will be several primitive elements for a given field. A finite field is a finite set on which the four operations multiplication, addition, subtraction and division, excluding division by 0, are defined, satisfying the rules of arithmetic known as the field axioms. The simplest examples of finite fields are the fields of prime order. For each prime number p, the field GF p, also denoted Z, PZ, F, P, display style mathbar F underscore P, or FP, of order, that is, size, P may be constructed as the integers modulo P, a more general algebraic structure that satisfies all the other axioms of a field, but whose multiplication is not required to be commutative, is called a division ring, or sometimes skew field. However, by Wedderburn's little theorem, any finite division ring must be commutative, and hence a finite field. The elements of such a field may be represented by integers in the range 0, p-1. The sum, the difference and the product are computed by taking the remainder by p of the integer result. The multiplicative inverse of an element may be computed by using the extended Euclidean algorithm. See extended Euclidean algorithm section. Modular integers. Let f be a finite field. For any element x in f and any integer n, let us denote by nx the sum of n copies of x. The least positive n such that n1 equals 0 must exist and is a prime number. It is called the characteristic of the field. If the characteristic of f is p, one can define multiplication of an element k of GF p by an element x of f k x display style k x maps to k c dot x by choosing an integer representative for k and using repeated addition. This multiplication makes f into a GF p vector space. It follows that the number of elements of f is Pn for some integer n. For every prime number p and every positive integer n, there exist finite fields of order Pn, and all fields of this order are isomorphic. See section existence and uniqueness below. One may therefore identify all fields of order Pn, which are therefore unambiguously denoted f, p, n. Display style mathbar f underscore p caret n. FPN a GF Pn, where the letters GF stand for Galois field. The identity x plus y p equals x p plus y p. Display style x plus y caret p equals x caret p plus y caret p. Sometimes called the freshman's dream, is true for every x and y in a field of characteristic p. This follows from each binomial coefficient of the expansion of x plus y p, except the first and the last, being a multiple of p, for each element x in the field GF. P. For a prime number p, one has xp equals x. This is an immediate consequence of Fermat's little theorem, and this may be proved as follows. The equality is trivially true for x equals 0 and x equals 1. One obtains the result for the other elements of GF. P. By applying Freshman's dreams with y equals 1 and x taking successively the values 1, 2, p minus 1 modulo p. This implies the equality x, p, minus x, equals a element of g, f, p, x, minus a. Display style x caret p x equals prod underscore a in room GF. P. Closing curly bracket. X a. Closing curly bracket. For polynomials over GF. P. More generally, every element in GF Pn satisfies the polynomial equation xPn minus x equals 0. Any finite field extension of a finite field is separable and simple. That is, if E is a finite field and F is a subfield of E, then E is obtained from F by adjoining a single element whose minimal polynomial is separable. To use a jargon, finite fields are perfect existence and uniqueness. Let Q equals Pn be a prime power, and F be the splitting field of the polynomial. P equals x q minus x. Display style P equals x caret q x over the prime field GF. P. This means that F is a finite field of lowest order, in which P has q distinct roots. The roots are distinct, as the formal derivative of P is equal to -1. The above identity shows that the sum and the product of two roots of P are roots of P, as well as the multiplicative inverse of a root of P. In other words, the roots of P form a field of order Q, which is equal to F by the minimality of the splitting field. The uniqueness up to isomorphism of splitting fields implies thus that all fields of order Q are isomorphic. In summary, we have the following classification theorem, first proved in 1893 by E. H. Moore. The order of a finite field is a prime power. For every prime power Q there are fields of order Q, and they are all isomorphic. In these fields, every element satisfies x q equals x. Display style x caret q equals x. Closing curly bracket, and the polynomial xq minus x factors as x q minus x equals a element of f x minus a. Display style x caret q x equals prod underscore a in f x a. Closing curly bracket. It follows that GF Pn contains a subfield isomorphic to GF Pm, if and only if M is a divisor of N. In that case, this subfield is unique. In fact, the polynomial xPm minus x divides xPn minus x if and only if M is a divisor of N. Explicit construction of the finite fields. Non-prime fields. Given a prime power Q equals Pn with P prime and N greater than 1. The field GF Q may be explicitly constructed in the following way. One chooses first an irreducible polynomial P in GF P x of degree n. Such an irreducible polynomial always exists. Then the quotient ring G F Q equals G F P X slash P. Display style room GF Q equals room GF P X slash P. Closing curly bracket of the polynomial ring GF P X by the ideal generated by P as a field of order Q. More explicitly, the elements of GF Q are the polynomials over GF P whose degree is strictly less than n. The addition and the subtraction are those of polynomials over GF P. The product of two elements is the remainder of the Euclidean division by P of the product in GF P X. The multiplicative inverse of a non-zero element may be computed with the extended Euclidean algorithm. See extended Euclidean algorithm section. Simple algebraic field extensions. Except in the construction of GF 4. There are several possible choices for P, which produce isomorphic results. To simplify the Euclidean division, for P, one commonly chooses polynomials of the form x, n, plus a, x, plus b. Display style x caret n plus ax plus b. Closing curly bracket, which make the needed Euclidean divisions very efficient. However, for some fields, typically in characteristic 2, irreducible polynomials of the form xn plus x plus b may not exist. In characteristic 2, if the polynomial xn plus x plus 1 is reducible, it is recommended to choose xn plus xk plus 1 with the lowest possible k that makes the polynomial irreducible. If all these trinomials are reducible, one chooses pentanomials xn plus xa plus xb plus xc plus 1 as polynomials of degree greater than 1, with an even number of terms, are never irreducible in characteristic 2, having 1 as a root. In the next sections, we will show how this general construction method works for small finite fields. Field with 4 elements. Over GF 2, there is only one irreducible polynomial of degree 2, x 2 plus x plus 1. Display style x caret 2 plus x plus 1. Therefore, for GF 4, the construction of the preceding section must involve this polynomial, and GF 4 equals GF 2 x slash x 2 plus x plus 1. Display style room GF 4 equals room GF 2 x slash x caret 2 plus x plus 1. Closing curly bracket. If one denotes, say, a root of this polynomial in GF 4, the tables of the operations in GF 4 are the following. There is no table for subtraction, because subtraction is identical to addition, as is the case for every field of characteristic 2. In the third table, for the division of x by y, x must be read on the left, and y on the top. GF P2, for an odd prime P. For applying the above general construction of the finite fields in the case of GF P2, one has to find an irreducible polynomial of degree 2. For P equals 2, this has been done in the preceding section. If P is an odd prime, there are always irreducible polynomials of the form x2 minus r, with r in GF P. More precisely, the polynomial x2 minus r is irreducible over GF P, if and only if r is a quadratic non-residue modulo P. This is almost the definition of a quadratic non-residue. There are P minus 1, 2, display style frac P1, 2, quadratic non-residues modulo P. For example, 2 is a quadratic non-residue for P equals 3. 5, 11, 13, and 3 is a quadratic non-residue for p equals 5, 7, 17. If p3 mod 4, that is p equals 3, 7, 11, 19, one may choose -1 p-1 as a quadratic non-residue, which allows us to have a very simple irreducible polynomial x2 plus 1. Having chosen a quadratic non-residue R, let alpha be a symbolic square root of R. That is a symbol which has the property alpha2 equals R. In the same way as the complex number I is a symbolic square root of -1. Then, the elements of GF P2 are all the linear expressions A plus B alpha, display style A plus B alpha, closing curly bracket, with A and B in GF P. The operations on GF P2 are defined as follows. The operations between elements of GF P, represented by Latin letters, are the operations in GF P minus A plus B alpha equals minus A plus minus B alpha A plus B alpha plus C plus D alpha equals A plus C plus B plus D alpha A plus B alpha C plus D alpha equals A C plus R B D plus A D plus B C alpha A plus B alpha minus 1 equals A 2 minus R B 2 minus 1 plus minus B A 2 minus R B 2 minus 1 alpha. Display style begin aligned A plus B alpha and equals A plus B alpha A plus B alpha plus C plus D alpha and equals A plus C plus B plus D alpha A plus B alpha C plus D alpha and equals AC plus RBD plus add plus BC alpha A plus B alpha caret minus 1 and equals A caret 2 RB caret 2 caret minus 1 plus B caret 2 RB caret 2 caret minus 1 alpha end aligned GF 8 and GF 27. The polynomial x3 minus x minus 1 display style x caret 3 x1 is irreducible over GF 2 and GF 3. That is, it is irreducible modulo 2 and 3. To show this, it suffices to show that it has no root in GF 2, nor in GF 3. It follows that the elements of GF 8 and GF 27 may be represented by expressions A plus B alpha plus C alpha 2 display style A plus B alpha plus C alpha caret 2 closing curly bracket, where A, B, C are elements of GF 2 or GF 3 respectively, and alpha display style alpha is a symbol such that alpha 3 equals alpha plus 1 display style alpha caret 3 equals alpha plus 1 closing curly bracket. The addition, additive inverse and multiplication on GF 8 and GF 27 may thus be defined as follows. In following formulas, the operations between elements of GF 2 or GF 3, represented by Latin letters, are the operations in GF 2 or GF 3, respectively, minus A plus B alpha plus C alpha 2 equals minus A plus minus B alpha plus minus C alpha 2 for G F 8. This operation is the identity A plus B alpha plus C alpha 2 plus D plus E alpha plus F alpha 2 equals A plus D plus B plus E alpha plus C plus F alpha 2 A plus B alpha plus C alpha 2 D plus E alpha plus F alpha 2 equals A D plus B F plus C E plus A E plus B D plus B F plus C E plus C F alpha plus A F plus B E plus C D plus C F alpha 2. Display style begin aligned A plus B alpha plus C alpha caret 2 equals A plus B alpha plus C alpha caret 2 Q quad text 4 Mathroom GF 8 text. This operation is the identity closing curly bracket backslash backslash A plus B alpha plus C alpha caret 2 plus D plus E alpha plus F alpha caret 2 and equals plus B plus E alpha plus C plus F alpha caret 2 A plus B alpha plus C alpha caret 2 D plus E alpha plus F alpha caret 2 and equals add plus BF plus Ch plus Air plus BD plus BF plus Ch plus CF alpha plus AF plus B plus CD plus CF alpha caret 2 end aligned GF 16. The polynomial x 4 plus x plus 1 display style x caret 4 plus x plus 1 is irreducible over GF 2. That is, it is irreducible modulo 2. It follows that the elements of GF 16 may be represented by expressions A plus B alpha plus C alpha 2 plus D alpha 3 display style A plus B alpha plus C alpha caret 2 plus D alpha caret 3 closing curly bracket where A B C D are either 0 or 1 elements of GF 2 and alpha is a symbol such that alpha 4 equals alpha plus 1 display style alpha caret 4 equals alpha plus 1 closing curly bracket. As the characteristic of GF 2 is 2, each element is its additive inverse in GF 16. The addition and multiplication on GF 16 may be defined as follows. In following formulas, the operations between elements of GF 2 represented by Latin letters are the operations in GF 2. A plus B alpha plus C alpha 2 plus D alpha 3 plus E plus F alpha plus G alpha 2 plus H alpha 3 equals A plus E plus B plus F alpha plus C plus G alpha 2 plus D plus H alpha 3 A plus B alpha plus C alpha 2 plus D alpha 3 e plus f alpha plus g alpha 2 plus h alpha 3 equals a e plus b h plus c g plus d f plus a f plus b e plus b h plus c g plus d f plus c h plus d g alpha plus a g plus b f plus c e plus c h plus d g plus d h alpha 2 plus a h plus b g plus c f plus d e plus d h alpha 3. Display style begin aligned. A plus b alpha plus c alpha caret 2 plus d alpha caret 3 plus e plus f alpha plus g alpha caret 2 plus h alpha caret 3 and equals a plus e plus b plus f alpha plus c plus g alpha caret 2 plus d plus h alpha caret 3 a plus b alpha plus c alpha caret 2 plus d alpha caret 3 e plus f alpha plus g alpha caret 2 plus h alpha caret 3 and equals a plus bh plus cg plus df plus af plus b plus bh plus cg plus df plus ch plus dg alpha plus and quad ag plus bf plus ch plus ch plus dg plus dh alpha caret 2 plus r plus bg plus cf plus d plus dh alpha caret 3 end aligned. Multiplicative structure. The set of non-zero elements in GF Q is an abelian group under the multiplication of order Q1 by Lagrange's theorem. There exists a divisor K of Q1 such that xk equals 1 for every non-zero x in GF Q. As the equation xk equals 1 has at most k solutions in any field, Q1 is the lowest possible value for k. The structure theorem of finite abelian groups implies that this multiplicative group is cyclic. That is, all non-zero elements are powers of a single element. In summary, the multiplicative group of the non-zero elements in GF Q is cyclic, and there exists an element A, such that the Q1 non-zero elements of GF Q are A, A2, AQ-2, AQ-1 equals 1. Such an element A is called the primitive element, unless Q equals 2, 3. The primitive element is not unique. The number of primitive elements is phi Q-1, where phi is Euler's totient function. The result above implies that xq equals x for every x in GF Q. The particular case where Q is prime is Fermat's little theorem. Discrete logarithm. If A is a primitive element in GF Q, then for any non-zero element x in F, there is a unique integer n with 0 n q-2 such that x equals n. This integer n is called the discrete logarithm of x to the base a, while n can be computed very quickly. For example, using exponentiation by squaring. There is no known efficient algorithm for computing the inverse operation, the discrete logarithm. This has been used in various cryptographic protocols. See discrete logarithm for details. When the non-zero elements of GF Q are represented by their discrete logarithms, multiplication and division are easy, as they reduce to addition and subtraction modulo Q1. However, addition amounts to computing the discrete logarithm of n plus n. The identity n plus n equals n minus n plus 1 allows one to solve this problem by constructing the table of the discrete logarithms of n plus 1, called Zek's logarithms, for n equals 0, q minus 2. It is convenient to define the discrete logarithm of 0 as being minus infinity. Zek's logarithms are useful for large computations, such as linear algebra over medium-sized fields. That is, fields that are sufficiently large for making natural algorithms inefficient, but not too large, as one has to pre-compute a table of the same size as the order of the field. Roots of unity. Every non-zero element of a finite field is a root of unity. As xq minus 1 equals 1 for every non-zero element of GF. Q. If n is a positive integer, an nth primitive root of unity is a solution of the equation xn equals 1 that is not a solution of the equation xm equals 1 for any positive integer m less than n. If A is a nth primitive root of unity in a field F, then F contains all the n roots of unity, which are 1, a2, and minus 1. The field GF Q contains a nth primitive root of unity if and only if n is a divisor of q minus 1. If n is a divisor of q minus 1, then the number of primitive nth roots of unity in GF Q is phi n. Euler's totient function. The number of nth roots of unity in GF Q is GCD n q minus 1. In a field of characteristic P, every np th root of unity is also a nth root of unity. It follows that primitive np th roots of unity never exist in a field of characteristic P. On the other hand, if n is coprime to P, the roots of the nth cyclotomic polynomial are distinct in every field of characteristic P. As this polynomial is a divisor of xn-1, whose discriminant n display style n, is non-zero modulo P, it follows that the nth cyclotomic polynomial factors over GF P into distinct irreducible polynomials that have all the same degree, say D, and that GF PD is the smallest field of characteristic P that contains the nth primitive roots of unity. Example: GF 64. The field GF 64 has several interesting properties that smaller fields do not share. It has two subfields such that neither is contained in the other. Not all generators, elements with minimal polynomial of degree 6 over GF 2, are primitive elements, and the primitive elements are not all conjugate under the Galois group. The order of this field being 26, and the divisors of 6 being 1, 2, 3, 6. The subfields of GF 64 are GF 2, GF 22 equals GF 4, GF 23 equals GF 8, and GF 64 itself, as 2 and 3 are coprime. The intersection of GF 4 and GF 8 in GF 64 is the prime field GF 2. The union of GF 4 and GF 8 has thus 10 elements. The remaining 54 elements of GF 64 generate GF 64, in the sense that no other subfield contains any of them. It follows that they are roots of irreducible polynomials of degree 6 over GF 2. This implies that, over GF 2, there are exactly 9 equals 54 sixths irreducible monic polynomials of degree 6. This may be verified by factoring x64 minus x over GF 2. The elements of GF 64 a primitive nth roots of unity for some n dividing 63. As the third and the seventh roots of unity belong to GF 4 and GF 8, respectively. The 54 generators are primitive nth roots of unity for some n in 9, 21, 63. Euler's totient function shows that there are 6 primitive ninth roots of unity, 12 primitive 21st roots of unity, and 36 primitive 63rd roots of unity. Summing these numbers, one finds again 54 elements. By factoring the cyclotomic polynomials over GF 2, one finds that the 6 primitive ninth roots of unity are roots of x6 plus x3 plus 1. Display style x caret 6 plus x caret 3 plus 1. Closing curly bracket. And are all conjugate under the action of the Galois group. The 12 primitive 21st roots of unity are roots of x6 plus x4 plus x2 plus x plus 1, x6 plus x5 plus x4 plus x2 plus 1. Display style x caret 6 plus x caret 4 plus x caret 2 plus x plus 1. X caret 6 plus x caret 5 plus x caret 4 plus x caret 2 plus 1. Closing curly bracket. They form two orbits under the action of the Galois group. As the two factors are reciprocal to each other, a root and its multiplicative inverse do not belong to the same orbit. The 36 primitive elements of GF 64 are the roots of x6 plus x4 plus x3 plus x plus 1, x6 plus x plus 1, x6 plus x5 plus 1, x6 plus x5 plus x3 plus x2 plus 1, x6 plus x5 plus x2 plus x plus 1, x6 plus x5 plus x4 plus x plus 1. Display style x caret 6 plus x caret 4 plus x caret 3 plus x plus 1. X caret 6 plus x plus 1. X caret 6 plus x caret 5 plus 1. X caret 6 plus x caret 5 plus x caret 3 plus x caret 2 plus 1. X caret 6 plus x caret 5 plus x caret 2 plus x plus 1. X caret 6 plus x caret 5 plus x caret 4 plus x plus 1. Closing curly bracket. They split into 6 orbits of 6 elements under the action of the Galois group. This shows that the best choice to construct GF 64 is to define it as GF 2 x/x6 plus x plus 1. In fact, this generator is a primitive element, and this polynomial is the irreducible polynomial that produces the easiest Euclidean division. Frobenius automorphism and Galois theory. In this section, P is a prime number, and Q equals Pn is a power of P. In GF Q, the identity x plus y, P equals xp plus yp implies that the map phi x p display style var phi x maps to x caret p is a GF P linear endomorphism and a field automorphism of GF Q, which fixes every element of the subfield GF P. It is called the Frobenius automorphism, after Ferdinand Georg Frobenius. denoting by phi k the composition of phi with itself k times. We have phi k x x p k display style var phi caret k x maps to x caret p caret k closing curly bracket. It has been shown in the preceding section that phi n is the identity for 0 less than k less than n. The automorphism phi k is not the identity as. Otherwise, the polynomial x p k minus x display style x caret p caret k x would have more than pk roots. There are no other gf p automorphisms of gf q. In other words, gf pn has exactly n gf p automorphisms, which are I d equals phi 0, phi 2, phi n minus 1. Display style mathroom id equals var phi caret 0, var phi caret 2, l dots, var phi caret n1. Closing curly bracket. In terms of Galois theory, this means that GF Pn is a Galois extension of GF P, which has a cyclic Galois group. The fact that the Frobenius map is surjective implies that every finite field is perfect. Polynomial factorization. If F is a finite field, a non-constant monic polynomial with coefficients in F is irreducible over F. If it is not the product of two non-constant monic polynomials with coefficients in F, as every polynomial ring over a field is a unique factorization domain. Every monic polynomial over a finite field may be factored in a unique way, up to the order of the factors, into a product of irreducible monic polynomials. There are efficient algorithms for testing polynomial irreducibility and factoring polynomials over finite field. They are a key step for factoring polynomials over the integers of the rational numbers. At least for this reason, every computer algebra system has functions for factoring polynomials over finite fields, or, at least, over finite prime fields. Irreducible polynomials of a given degree. The polynomial x q minus x display style x caret q x factors into linear factors over a field of order q. More precisely, this polynomial is the product of all monic polynomials of degree 1 over a field of order q. This implies that if q equals Pn, then xq minus x is the product of all monic irreducible polynomials over GF P, whose degree divides n. In fact, if P is an irreducible factor over GF P of xq minus x, its degree divides n, as its splitting field is contained in GF Pn. Conversely, if P is an irreducible monic polynomial over GF P of degree d dividing n, it defines a field extension of degree d, which is contained in GF Pn, and all roots of P belong to GF Pn, and the roots of xq minus x. Thus P divides xq minus x. As xq minus x does not have any multiple factor, it is thus the product of all the irreducible monic polynomials that divide it. This property is used to compute the product of the irreducible factors of each degree of polynomials over GF P. See distinct degree factorization. Number of monic irreducible polynomials of a given degree over a finite field. The number n, q, n of monic irreducible polynomials of degree n over GF Q is given by n q n equals 1 n d pipe n mu d q n d. Display style n q n equals frac 1 n sum underscore d n mu d q caret frac n d closing curly bracket, where mu is the Mobius function. This formula is almost a direct consequence of above property of xq minus x. By the above formula, the number of irreducible, not necessarily monarch, polynomials of degree n over gf q is q minus 1 n q n a. Slightly simpler, lower bound for n q n is n q n 1 n q n minus p pipe n p prime q n p. Display style n q n geq frac 1 n left q caret n sum underscore p n p text prime q caret frac n p right closing curly bracket. One may easily deduce that for every q and every n, there is at least one irreducible polynomial of degree n over gf q. This lower bound is sharp for q equals n equals 2. Applications. In cryptography, the difficulty of the discrete logarithm problem in finite fields or in elliptic curves is the basis of several widely used protocols, such as the Diffie-Hellman protocol. For example, in 2014 a secure internet connection to Wikipedia involved the elliptic curve Diffie-Hellman protocol, ECDHE, over a large finite field. In coding theory, many codes are constructed as subspaces of vector spaces over finite fields. Finite fields are widely used in number theory, as many problems over the integers may be solved by reducing them modulo 1 or several prime numbers. For example, the fastest known algorithms for polynomial factorization and linear algebra over the field of rational numbers proceed by reduction modulo 1 or several primes, and then reconstruction of the solution by using Chinese remainder theorem, Hensel lifting of the LLL algorithm. Similarly, many theoretical problems in number theory can be solved by considering their reductions modulo some or all prime numbers. See, for example, Hasse principle. Many recent developments of algebraic geometry were motivated by the need to enlarge the power of these modular methods. Weil's proof of Fermat's last theorem is an example of a deep result involving many mathematical tools, including finite fields, extensions, algebraic closure. A finite field F is not algebraically closed. To demonstrate this, consider the polynomial f t equals 1 plus alpha, element of f t minus alpha. Display style f t equals 1 plus prod underscore alpha in math BF f t alpha closing curly bracket, which has no roots in f. Since f alpha equals 1 for all alpha in f, the direct limit of the system fp, fp2, fpn, closing curly bracket, with inclusion, is an infinite field. It is the algebraic closure of all the fields in the system, and is denoted by fp. Display style overline math BF f underscore p. The inclusions commute with a Frobenius map, as it is defined the same way on each field xxp. So the Frobenius map defines an automorphism of f p. Display style overline math BF f underscore p, which carries all subfields back to themselves. In fact, fpn can be recovered as the fixed points of the nth iterate of the Frobenius map. However, unlike the case of finite fields, the Frobenius automorphism on f p display style overline math BF f underscore p has infinite order. and it does not generate the full group of automorphisms of this field. That is, there are automorphisms of f p display style overline math BF f underscore p, which are not a power of the Frobenius map. However, the group generated by the Frobenius map is a dense subgroup of the automorphism group in the Krull topology. Algebraically, this corresponds to the additive group Z being dense in the profinite integers. Direct product of the p-adic integers over all primes p, with the product topology. If we actually construct our finite fields in such a fashion that Fpn is contained in Fpm whenever n divides m, then this direct limit can be constructed as the union of all these fields. Even if we do not construct our fields this way, we can still speak of the algebraic closure, but some more delicacy is required in its construction. Wedderburn's little theorem. A division ring is a generalization of field. Division rings are not assumed to be commutative. There are no non-commutative finite division rings. Wedderburn's little theorem states that all finite division rings are commutative, hence finite fields. The result holds even if we relax associativity and consider alternative rings. By the Artin-Zorn theorem, relationship to other commutative ring classes, finite fields appear in the following chain of inclusions. Commutative rings, integral domains, integrally closed domains, GCD domains, unique factorization domains, principal ideal domains, Euclidean domains, fields, finite fields. See also quasi-finite field, field with one element, finite field, arithmetic, trigonometry and Galois fields, finite ring, finite group, elementary abelian group, Hamming space. Notes. W. H. Bussey. 1905. Galois field tables for PN 169. Bulletin of the American Mathematical Society 12. 1. 22-38. DOI. 10.1090, S0002, 9904, 1905, 01284, 2. W. H. Bussey. 1910. Tables of Galois fields of order less than 1000. Bulletin of the American Mathematical Society 16. 4. 188-206. DOI. 10.1090, S0002, 9904, 1910, 01888, 7. Jacobson, Nathan. 2009. 1985. Basic Algebra I. 2nd ed. Dover Publications. ISBN 978-0-486-47189-1. Mullin, Gary L. Mummett, Carl. 2007. Finite Fields and Applications I. Student Mathematical Library. AMS. ISBN 978-0-8218-4418-2. Mullin, Gary L. Panario, Daniel. 2013. Handbook of Finite Fields. CRC Press. ISBN 978-1-4398-7378-6. Liddell, Rudolph. Niederreiter, Harold. 1997. Finite Fields. 2nd ed. Cambridge University Press. ISBN 0-521-39231-4. Finite Fields at Wolfram Research.